All right, guys. So today we are going to move on to doing applications of exponential functions. So we've spent the past several classes discussing solving exponential equations that have like bases, and now we're transitioning into actual applications of those particular functions. This is going to be especially useful because if there's one takeaway important thing for you guys in quote adult world, it's understanding exponential functions, because these exponential functions are used for appreciation and depreciation, exponential growth and decay, and what's most important for you guys, compounding interest and continuously compounding interest. Because as you get older and you start making financial decisions, we're talking about things as complicated as buying a house, to leasing a car, to buying furniture and putting it on a payment plan. All of this stuff is going to be incredibly useful. And I will say that a lot of banks and lending institutions tend to prey on the mathematically ignorant, because they will say one thing and it's not entirely accurate, or it's not the complete picture. So having a solid understanding of how this stuff all works together is like actually super duper important to real world survival skills. So appreciation and depreciation. Hopefully we've heard those words before, and we know that when things appreciate, they gain value, and when things depreciate, they lose value. That goes along with exponential growth and decay, where it's getting larger or getting smaller. Compounding interest, that is what we call periodic. Okay. Okay. So periodically compounding interest. So you're going to come across certain words and phrases that mean different things. We'll talk about that in a minute. And then you also have continuously compounding interest. If you have continuously compounding interest, that is going to use a base of the natural number e. Okay. We're going to be using our calculator for e, but we can go through and approximate e, um, and we can approximate it at about 2.72 or 2.718. But we can use this in case you have a calculator that doesn't have the E button. But if it says continuously, it means you need to use E. Okay. So what are the formulas that we're going to be using for these different exponential growth or exponential decay or compounding or continuously compounding interest? So all of those formulas are right here. Okay. So we have what's called the appreciation formula and the depreciation formula. Okay. You'll notice that there's something very similar between them, in that they look almost exactly the same. The only real difference is with appreciation, we are adding value over time, whereas with depreciation, we are losing value over time. So make sure that you look at that with a scrupulous eye to make sure that you don't accidentally say something's growing, but then you take away value, or that something's losing value, but in fact you're making it add it. Okay. The generalized formula for what we call exponential growth is y equals a times e raised to the kt. Okay. K is your growth factor, t is time, E is the natural number E, and A is your initial amount. We're going to go over what all of these mean in just a minute. Okay. But this is your generic exponential growth formula. Okay. If we're dealing with money, which is why the text is in green, we could be dealing with compounding interest, which this is periodically compounding interest, or continuously compounding interest. They are two different formulas. Okay. Two different formulas. For our periodically compounding interest, it's a equals p times 1 plus r over n raised to the nt. For continuously compounding interest, it's a equals p times e raised to the rt. So you'll notice some things are the same. They both have this value p, okay? This one over here is raised to the nt. This one over here is raised to the rt. The exponential base over here is whatever 1 plus r over n is, but the exponential base here is the natural number e. Okay, so they're similar, but obviously different. The other thing that I want you to notice is that the continuously compounding interest formula is exactly the same as the exponential growth formula. It's just a different context. Okay, in this context, okay, we have a starting amount and a growth factor. In this context, we have a principal and an interest rate. So they're effectively the same thing, just with different context. All right. So again, we have appreciation, we have depreciation, we have exponential growth, we have periodically compounding interest, and we have continuously compounding interest. All right. So within each one of these formulas, there's lots of different variables. What do they all mean? This A, this R, this T, this K, this N, this P. What the heck does that all mean? Okay. And that's why we've got on the next page your variable definitions. Okay. So for each one of those formulas, A would represent the initial amount if it's a non-money type of problem. Capital P represents the principal amount. That's if you're dealing with money. In finance, principal is always your starting amount, your initial investment. Okay. You walk into a bank with $100 bill and say you want to open up a savings account, then $100 is your principal. Okay. That's also why if you guys look at any sort of investment literature where it goes and gives you the warning, the disclaimer that, all investments involve risk, including loss of principal, that essentially means that you could go through and you could lose everything that you put into it. There's no guarantee that you are going to always have the principal that you put in. Whereas with other types of investments, you're guaranteed to never lose that principal. Think about like a generic savings account, okay? Unless you make the withdrawal, they're never going to take that principal away from you, okay? Also, if we're dealing with money problems, capital A is the final amount, okay, or the account balance at the end. If we're dealing with non-money problems, then we just use a generic Y, okay, because it's a function, so Y equals kind of makes sense, okay? R or K represent the rate of interest or of growth or decay, okay? With growth and decay, it's really growth is positive, decay is negative, but we always have to go and express that as a decimal, okay? So, for example, say that you had a growth or decay rate and it was listed at 2.75%. You can't use it as a percent. You have to convert it into a decimal. So hopefully we all remember that converting percents into decimals simply involve moving the decimal place over 2 units to the left. So this would be equivalent to 0.0275. Okay, so we cannot use percents, although percents are pretty much what's given in every problem. We have to convert all of those to decimals. Please make sure that you're being careful with that, because if you forget to move it over 2 decimal places, well, then you just said you have like 20.75% interest, which is substantially different than 2.75% interest. Okay. T, generally speaking, is time in years. Okay. Unless otherwise indicated. If it's otherwise indicated that time is being measured in, months or decades or centuries or weeks, T is time, years is the default unless it's otherwise indicated. Okay. In the last variable that we got to make sure that we understand is the frequency of compounding. Okay. So that could be it compounds once, compounds twice, 4 times, 6 times, 12 times, 365 times, etc. Generally speaking, those are going to come from your banking type problems, and I'm going to give you a little chart that you can use to kind of diagnose what each one of those different values means. So if you see the word yearly, that means its compounding frequency is 1, okay? Essentially, that means that in a year, you're calculating interest one time. Okay. If you see the word semi-annual, okay, that means twice in a year. Okay. So semi-annual compounding interest or interest compounding semi-annually means that you're collecting interest twice in a year. So the frequency of compounding is 2 when you see semi-annual. Okay. The next one we have is quarterly. And that's going to represent 4. Kind of makes sense. There's 4 quarters in anything. So quarterly compounding interest is 4. 6 is what we call bi-monthly. All right. So that means every 2 months. You're not really going to see a lot of bi-monthly compounding interest. It doesn't happen very frequently. I just wanted to go and make sure that we understood that bi-monthly is 6 and not 24. Okay, it's not twice per month. It's every 2 months. All right. So then going beyond that, we have 12, which if you had to take a guess, hopefully you're all thinking monthly. Okay, there's 12 months in a year, and then 365 would be daily. Okay, so a lot of times in the problems, you're going to see the words, and you have to convert the words into these particular numbers for the frequency of compounding. So again, 1 is yearly, 2 is semi-annually, 4 is quarterly, 6 is bi-monthly, 12 is monthly, and 365 is daily. All right, if you have continuously, that is going to use a base of E, okay? And that's a completely different formula, all right? So continuously is you're using the continuously compounding interest formula, not a periodically compounding interest formula, all right? So let's take a look at what we've done, okay, with all our different little formulas. And the good news is the rest of this is pretty much plug and chug. It's kind of nice. So if we go take a look at example 1 here, it says, on the day you were born, your grandpa started a college savings account for you. Your grandparents, sorry, they deposited $5,000 in a TDA, which is a time deposit account, with 3.75% interest compounded quarterly. How much is in the account on your 18th birthday? All right, so the first thing we need to do when we're looking at these problems is figure out what kind of problem is this? What formula should I be using? Okay, so it says you've got an amount that's been invested and it's being compounded quarterly. So we're going to want to use the periodically compounding interest formula. Okay, so let's go ahead and put down the appropriate formula that we should be using for this problem. So if you look back at the other pages in your notes, you're going to see that the formula for periodically compounding is A equals P times 1 plus R over N raised to the NT. So I need to go and pull as many of those different values out of the question as I can. So I'm going to look in here and say that they deposited $5,000. So that's got to be your initial investment. Okay. It's got a 3.75% interest rate. Well, that's got to be your rate. And it's being compounded quarterly. So that's got to be your value for T. All right. So let's go and put in what it is that we need to know and what it is that we do know. So if we're going to figure out how much is in the account on your 18th birthday, which that 18th birthday is also something that's important, okay? Because that's obviously 18 years after the day you were born. So we need to know what P is, we need to know what R is, we need to know N, and we need to know T. So P is your principal. Well, how much did your grandparents put in your college account? $5,000. How nice of them. Give them a big hug. Okay. Your interest rate is 3.75%, but I can't write 3.75%. I have to convert that into a decimal. So that's 0.0375. Okay, move that decimal place over twice. N is the frequency of compounding. It says quarterly, so the value of N is 4. And then T is the amount of time that has passed. Well, how much time has passed? 18 years. Okay, so we have this particular formula, and it's time to start looking at this problem. All right, so let's go and plug all of those values in. So we have A equals P, which is 5,000, times 1 plus our interest rate was 0.0375 over N, which is 4 because it's quarterly, and we're going to raise that to the NT. So 4 times 18. Okay, this is plug and chug. We're going to go and plug this into our calculator now. Okay, so what I want you guys to do is we're all going to type in to your calculator 5,000 parentheses 1 plus another set of parentheses 0.0375 divided by 4, close parentheses, and another close parentheses. Caret key, or go to the exponent, and then we're going to type in 4 times 18. You may need to put the 4 times 18 in a set of parentheses depending on what calculator you're using. Fancy calculator, you can just do 4.18. Older calculator or just a basic TI-30, you're going to want to put it in parentheses. Okay, hit enter. You should get that the amount that is in this particular account after 18 years is $9,879.33. Okay. If you didn't get that, let me know, and I'll ask you to kind of walk me through what you put into your calculator, and we'll kind of go from there. But plugging this just into the calculator, we're going to get that the initial amount was $5,000, and after 18 years, it was worth almost $10,000. Pretty good deal, okay? So thanks, Grandma and Grandpa. All right, so the next thing says if the account accrued interest monthly, how much more would be in the account? So now we're making a comparison. All the values are the same except we're changing one, okay? We're changing the value of N this time to be 12. So N is 12 instead of 4. So our interest rate is still the same, okay? Our time is still the same, it's still 18 years, and our principal is still the same at $5,000. Okay, so how much is in this account? Well, plug and chug. A equals P, so that's 5,000, times 1 plus 0.0375 over now 12 because it's monthly, raised to the 12 times 18. Okay, so let's go and plug that into your calculator. You should end up doing that, getting $9,809.83. Okay, so how much more would be in the count? Well, just do a subtraction problem. $9,809.83 minus $9,879.33 is a difference of $20.50. Okay, so there's $20.50 more if the account had interest that was compounded monthly instead of interest that was compounded quarterly. Now, in the big scheme of things, is that really that big of a difference? Not so much. But when you start talking about investing at larger and larger numbers, like we're talking, Elon Musk, Jeff Bezos kind of numbers, well, If you go and move this decimal place over, 3 or 4 points over to the right, well, then you'd be moving this number 3 or 4 decimal places over to the right. And then you're starting to talk about a little bit um, bigger values there, so they might be slightly more important. Okay, so we're going to go and run through a few more examples. Stick with me. It's going to be a longer class today, but that's all good. So, example 2. It says an investment of $25,000 is made into an account that compounds interest semi-annually. After 5 years, the account is worth $34,214.56. What is the annual interest rate on the account? Ooh, so this one is a little bit different because it's not asking for a final amount. They give us the initial investment. They give us the frequency of compounding. They give us the time, and they give us the ending amount. But what they don't give us is the interest rate. So mathematically, how can I go and figure this one out? Well, first I need to know which formula I'm going to use. Okay, well, obviously this is periodically compounding interest because it's got the word semi-annually. So we're going to be using not P, A. A equals P times 1 plus R over N raised to the NT. Okay, so let's write down what we know. We know P, okay, that's $25,000. We do not know R. That's what we're trying to actually go through and find. We know that N is 2 because it says the word semi-annually. We know that T is 5 because it's 5 years. And we also know that the final amount is $34,214.56. So let's plug in what we know to try and solve for what we don't. So we have $34,214.56, and that equals $25,000 times 1 plus an unknown R over 2 raised to 2 times 5. Okay, so the first thing that we need to do is realize that we're trying to solve for R. R is trapped in this set of parentheses. Okay, this set of parentheses has 2 operations connected to it. It's got exponents, but it's also got multiplication. Remember though, when we're solving, we always use reverse order of operations. So I would need to start by dividing each side by $25,000. Okay, so this $25,000 divided by that $25,000, those divide out, and we're going to end up with some value over here. Okay, so I'm going to go and write it to an obscene number of decimal places, just because that's going to make it slightly more accurate. So we really want to go and write a lot of decimal places and not just go to 1 or 2. Okay, so if you use your calculator and do 34,214.56 and divide that by 25,000, you're going to get 1.368582 okay, so like 1, 2, 3, 4, 5, 6, 7 decimal places. So a lot, but we kind of want that. That's going to be equal to 1 plus R over 2 raised to the, go ahead and do 10th. Okay, so the R is still trapped inside the set of parentheses. And why is there a set of parentheses? Because you're raising it to the 10th. So I'm going to go ahead and show you guys something. It's going to be using exponent rules again. But if this was a 2, it would be squared, and you would get rid of it by taking the square root. If this was a 3, it would be cubed, and you'd get rid of it by taking a cube root. But this is a 10. So how do you take a 10th root? Well, the easiest way to do that is just to raise it to 1/10. Okay, it's reciprocal. So if I do that to the left-hand side of the problem, I also need to do that to the right-hand side of the problem. So if I have something that's raised to the 10th and I raise it to the 1/10, well then power of a power property says 10 times 1/10 is really just 1. So those just kind of power themselves out. This over here obviously has to get done in a calculator. But if you go and do 1.3685824 and raise all of that to the 1/10, again, use your calculator here, folks, we're going to get 1.03187 okay? And that's going to be equal to 1 plus r over 2. So now it should be a little easier to solve for r. I'm going to subtract 1 from both sides, okay? So I get 0.03187 equals r divided by 2. Then I'm just going to multiply each side by 2, okay? Because that's how I'm going to get rid of the divided by 2 part. And if I multiply the left side and the right side by 2, I get 0.06375 equals r, okay? But it asks me for the annual interest rate on the account. Well, this is as a decimal, but I want to go and do this as a percentage. So I would need to say that the rate is, move the decimal place 2 units in the opposite direction, 6.375%. Okay, so kind of a longer problem, but that's okay. It's a lot of plug and chug stuff, right? The next one we're going to do is going to be a little bit simpler because this is going to be basic appreciation depreciation. So example 3 says you buy a new car valued at $38,850. The car depreciates at a rate of 12% per year. How much is the car worth after 4 years? So we'll go into turbo mode here. So the new car has an initial value of this. You know that its rate is 12% per year, and that is a rate of depreciation. You're trying to figure out how much the car is worth in about 4 years' time. So because you see the word depreciate, we know that this is the depreciation formula, okay? So what formula am I using? Y equals A times 1 minus R raised to the T, okay? So what is the value of A for this problem? 38,850. What is the value of R? Well, it's 12%. That's 0.12, okay? 12%, move the decimal place twice. T is 4 because we're talking about 4 years. So let's use those values and plug them into the formula. So Y equals 38,850 times 1 minus 0.12 raised to the 4. Well, if we do the operation that's inside the parentheses first, we're going to get 38,850 times 0.88 raised to the 4, okay? Plug that into your calculator and you're going to get that Y is equal to $23,298.16, okay? So your almost $40,000 car is worth just a little over $20,000 4 years after you buy it if it's depreciating at 12% per year, okay? Now, the one thing that I do want to show you guys is the other reason that you can tell that this is depreciation. When you look at what's inside the parentheses here, this one minus 0.12, we simplify it and we get 0.88, okay? That means that each year the car is only worth 88% of what it was worth in the previous year. So this is kind of a segue into what we're going to be taking a look at next, which is identifying through just visual inspection, is something exponential growth or is it decay, without needing to understand or see the kind of critical words that are there, all right? So example 4 says, determine if the following equations represent exponential growth or decay. So we need to remember that growth, okay, growth, we always have like 1 plus an interest rate. So growth is always greater than 1 because 1 plus something is bigger than 1. If we have decay, well, that's always coming from 1 minus r. So decay is always going to be less than 1. Well, what if it equals 1? Well, if the base is 1, it's not an exponential function, so I don't got to worry about it. So what I'm going to be doing is I'm going to be looking at the value that is inside that is about to be raised to a certain exponent, okay? And that's going to dictate to me whether it is growth or decay. So for this first problem, we have a factor of 0.5 that's getting raised to an exponent. Well, zero point 0.5 is less than 1, ergo this one is decay. For example B, we have 1 plus 0.012. Well, that's 1.012. Well, that's greater than 1, so that one is going to represent growth. When we look here, we see that this looks like kind of continuously compounded. We got this 200 times e raised to the something times something. Well, remember, what does e approximately equal? Well, e is approximately 2.72, and 2.72 is greater than 1, so this is obviously growth. And then for our last one here, we have a base, an exponential base of 0.95. Well, 0.95 is less than 1, so this one must be decay. Okay, so just through visual inspection, a lot of times we can tell, is this going to be getting bigger? Is this going to be getting smaller? Okay, so the last thing that we're going to go and take a look at is interpreting these types of problems through context and understanding what each value represents. All right, so we're going to take a look at this, and I'm going to go grab my little function and drag it over here so you guys can actually see it. But looking at this problem, for example 5, it says, since 2001, the town of Examplesville has grown according to the formula P of x equals 81,786 times 1.011 raised to the x, where x represents the number of years since 2001. All right, so look at that problem. What can you tell about it? What can you not tell about it? And that's really what going through these 4 parts is going to be. So the first part is asking us to explain what the number 81,786 means. Well, that's this guy right here. If we think about things in terms of exponential growth and decay, increasing, decreasing, the first value, that constant value there, that's always kind of your principal or your starting amount. So what does this mean? This is the population of Examplesville Okay, but when was it the population of Examplesville? Well, X represents the number of years since 2001. So if X was 0, well, that would mean that it was in 2001. So it is the population of Examplesville in 2001. Okay, we could also call that the initial population, although I'm pretty sure 81,786 people didn't just spontaneously appear, but that's going to be kind of the starting point for where they're looking at this growth model. The next part says explain what the number 1.011 means. So that's this part right here, okay? So that 1.11, well, we know that what's inside of here, okay, is generally speaking 1 plus r. So if 1.011 equals 1 plus r, then we could deduce that r is actually 0.011, which is really a 1.1% growth rate. Okay, so the number 1.011 is the rate of exponential growth for the town of Examplesville. And again, just by looking at it, you can tell me exactly what the growth rate is, doing some basic addition and subtraction and converting from a decimal into a percentage. Okay, so C says, what would the population be in 2020? Well, this is where we got to take some things into context. So when we look at the value of X, okay, X is years since 2001. Okay, so in the year 2020 to the year 2001, how much time has passed? Okay, well, that indicates that T would be equal to 19. Because if you add 19 years to 2001, you get to 2020. Do not just go and plug 2020 into this problem, because that would be 2020 years after 2001. Okay, and at the rate we're going, we might not really have a planet anymore at that point. So, maybe let's stick with 19 on this one. So, what would the population be in 2020? Well, we can plug in the value of 19. So, 81,786 times 1.011 raised to the 19th, and again, this is going to be calculator work, that is going to equal 100,681 people. Okay, you'll notice that I did not include a decimal on that, but there was a decimal when I went through and ran the calculations. Why didn't I include a decimal? Why did I just round? The short answer is you can't have fractional people. You either are a person or you're not. There's no like, oh, well, you're really short, so you're only like 0.7 of a person. Oh, here's an amputee. Well, you're like 0.95 of a person. That's not how it works. You are a whole person. So we need to exclusively use whole numbers when we're counting anything that involves a living organism, but most especially people. Okay, so the last part of this question is the one where it's really going to be stuff that we're going to look at more specifically later in this unit. But it's asking me to estimate the year in which the population will reach 110,000 if the model holds. So when you see estimate, what that really means is take some guesses. All right, so I'm going to go ahead and say, well, maybe let's start at, I don't know, we know in 2020 we're at 100,000 people and it's growing like 1% every year. So, I mean, maybe if I go like 10 years past that, maybe I should go and see about maybe doing something like that. So we're literally just guessing. So we're going to say 81,786 times 1.011, and 10 years past 2020 would be 2030. So that would be at like 29. Okay. So if you go and grab your calculator and we start trying to plug that in, we're literally just guessing and checking. So we're hoping to get close to a particular number. That number that we're hoping to get close to is 110,000, but let's go plug this in. So if we did 81,786, sorry, 81,786, helps if you type in the right numbers, times parentheses 1.011, and we're going to go and raise that to the 29th. Well, that's 112,000. Okay, so that's 112,322 people. Okay, because we're rounding up. All right, well, that's not 110,000, so maybe we got to go less than that. So 81,786 times 1.011. Let's go 2 years prior. Okay, let's go 27. Okay, so if I go and plug that in and type in 81,786 times 1.011 and raise that to the 27th, well, I'm going to get 109,890. Well, that's pretty close, okay? But maybe let's go and just make sure we can't get any closer to that. So let's do 1.011 and we'll raise it to the 28th, okay? So if I go and instead of raising it to the 27th, I raise it to the 28th, I'm going to get 111,099. So which one of those is the closest? Probably that one. Okay. So if we have a value where t is 27, okay, that's going to be 27 years after 2001. So, in 2020, it was 19 years. So if we go and add, how many years to that? 8 years to that, we'll get the closest. So we would say about 2028, okay, the population will reach 110,000 at that point. Okay, so later on we'll actually learn how to get an exact value for that when we start doing logarithms, but this is literally just some guessing and checking. Um, Now, why would this be something important? Well, maybe you're in charge of the municipal water supply, and your system can currently handle about 110,000 people, and it's 2001, and you've got 81,000 people in the town. Well, if you're trying to plan for growth, you don't want to wait until you go over 110,000 people and then start trying to build a new water treatment plant. You want to kind of have it ready to go before that happens. So sometimes doing these types of estimations is going to be important. All right, so I realize that this has been a really long lesson. I appreciate you guys hanging in there. Um, and now you can go take a look at some of your Delta Math assignments and let's see what we can figure out with those.